So the problem actually comes from the time I was at Microsoft. What happens typically when new area arises in the programming language, what people do, if you are there, you have some favorite language, maybe Java, maybe whatever, and you try to build on what you like. And as a rule, it is kind of wrong, because there are certain languages which are naturally appropriate. So it was one of my disappointments in the end of my Microsoft career, because Microsoft, when this craze phase started to throw enormous amount of money on quantum computing, hire people, and as usual, things didn't move as far as quantum physics as fast as expected. And what Microsoft typically does in such cases, you write software. So when the physics will be ready, we're ready with our software. And I started a new language, and I felt it's not the right thing to do, but I can just from out of the bat, propose a new language. You need to kind of think about it. So it eventually occurred to me, it took years to write it down, but today I will present it to you. So as many of, this is one of the papers in the Bulletin of European Association for Theoretical Computer Science, where I have a column on logic and computer science. And I typically write as a conversation with the students. So Q is Quizani, my former student. A is the authors. And it came from necessity. If you're good writer, you don't need help. If you're a poor writer, if you need how segue from one topic to another, it's hard. But if it's a dialogue, the other guy can just ask any question he wants and changes topics relatively gracefully. Okay, so there are two authors here. So we say, speaking one at a time. On the abstraction level of quantum circuits, diagrams, quantum circuits algorithms are just normal classical algorithms. And Quizani say, wait a second, they're classical, not quantum. If anything, not quantum, it's classical. So what do you do with measurements and all this? Okay, you'll see. So this is overview. So I'll have to explain what are traditional kind of classical algorithms, and then recall what quantum circuit algorithms are exactly. And at the end, show the quantum circuit algorithms are essentially classical sequential algorithms. Okay, here's an example of Euclid's algorithm. Given integers, A at least as large as B, compute the common denominator. So this is a little updated version. Euclid himself used not mod, but difference. So this version is exponentially time faster, but as algorithms concerned, very similar. So this is in terms of abstract state machines. I'll later explain the syntax. I want to, even in this simple case, I want to show people often come, whatever they do in theoretical computer science, there's an appropriate Turing machine. But Turing's analysis was, it was wonderful analysis. I was champion of Turing for decades. And because for logicians, it's Church's thesis, not Turing's thesis. And then suddenly Turing became so famous. So now I moved to another camp, showing off that he didn't do everything. So for example, And Turing machines don't interact with the environment, just computes there, live in the vacuum. Okay. But somebody who should compute that mod. Yeah, how? So what happens when in a normal programming language you say A mod B? Now, what does it mean? Essentially, it's a cry for help to operating system, or in general to the environment. And the environment does what is expected to do, and you proceed. And if not, there are some errors. But it's very important that any algorithm always interacts with environment. It's implicit. We just abstract from it, but it is there. And for my reasons today, it will be very important. Another small thing is a higher level of abstraction. So you can do this on Turing machines, but you don't want to. So another algorithm, a ruler and compass, also comes from us from roughly the same times. So let me explain now. So we're given this little circle centered around P and another point. So these are all givens. Circle C centered at P and point Q. And the task is to find a tangent using only a ruler and compass. By the way, concerning this ruler and compass, you say, why ruler and compass? In Greek, realize that there is a ellipsis. Oh, they knew ellipses. They were very sophisticated. But they didn't have a good tool. So, no, it's a wrong lecture, but the Greeks essentially made a revolution in logic and philosophy and many things. But in almost any kind of mathematics, there were some other civilizations which were better than them. In geometry, Egyptians were better. But for Egyptians, it was a very important practical purpose to, once almost every year, the Nile would overflow. And then you have to divide the land. And so it was a practical need, and they developed algorithms to deal with this. For Egyptians, those algorithms were about the land. But Greeks, with their philosophy, they realized that there is something more abstract here. Similarly, Babylonians were better than Greeks in algebra. But the Greeks had, due to democracy, by the way, because in all those cultures, you go to temple and all this secret, all this knowledge is between you and God, and priest and God. And in democracy, you have to convince your fellow citizens. And you, therefore, logic and rhetoric. Forgot the term. There was another kind of convincing when you play on the kind of populist and you play on the lower feelings of the crowd. But that's part of convincing. And that was all developed there. Okay, so they used the compass and ruler as practical. That was their computer. That's why it was, for them it was so important. It was practical computer of the Greeks. Now, so here is the solution. First, you draw the midpoint. So that by itself is a problem which needs to be solved, but we assume we know how to do that. Then you draw a circle around this midpoint through P and Q. Then there are two intersection points, and you choose one. Notice, non-determinism is coming. You have to choose one of two. It doesn't really matter. It's all automorphic. Mathematically, it's just the same thing. Nevertheless, you have to choose one of the point. Say you choose. Oh, sorry. Suppose you choose this point, and then you draw a line from Q and S, and this is a desired tangent. So what are the beyond Turing aspects here? One is non-symbolic nature. If you read Turing's paper, then the most interesting part where he justifies his thesis. Not very carefully. It's not the modern philosophers which read their papers. He just writes with white brush, makes bold assignments that our mind could be in finite many states. That's one of the things he relies on. But the very first sentence in that kind of extremely impressive stroke of genius, it only goes for a couple of pages. He starts with algorithms are, let me see. We compute by moving around symbols. It's not quotation, I forgot quotation, but that's the gist of it, that we compute symbolically, writing symbols, moving them, and so on. Now, this is definitely not symbolic. And Turing analysis does not apply to these algorithms directly. Now, you can use algebra to make coordinates and eventually prove that Turing can approximate all this. But directly, Turing analysis does not apply to these algorithms. So that's non-symbolic nature. And another thing is non-determinism. By the way, non-determinism is definitely not algorithmic. So in the United States, there is this baseball philosopher, Yogi Berra. So one of his statements is, if you come to a fork in the road, take it. Here's your algorithm. Now what? That's what non-deterministic algorithm is. So there's no such thing. It's a contradiction in terms, if you really think about it. Now, of course, we can define red herring is not red and not herring. So we can define non-deterministic algorithms as a separate notion, but it will not be algorithm in the way classically algorithms were understood. Okay. This actually not so important. I work like nature in biology. You know, nature doesn't invent anything twice. Whatever is invented is used, reused, reused over. That's why we all have more or less the same organs with other animals, and not only animals. So I use the slide. So this slide is essentially, this is the slide that made Microsoft to invite me. So so what is the problem? So how in industry, how it works? You have some idea. You want to prove kind of want to do some system which does something. Okay. Maybe very informal. So you start on somewhere up. Sorry. Start somewhere here. Then you refine it, add details, make it more precise. So eventually you are quite precise, but on a high level abstraction. Then you go down, refine. Then you come to a level where you can code. This level depends on the how high level is your language. So, but in industry, they often go quite low, typically to C++, and before that to C, because higher language is more convenient to program, but there is a price. It's in efficiency. But never mind what the language is. Now you code, and now you test. You test small units, bigger units, bigger units. Now imagine you just somewhere there you discover a problem. You couldn't see this problem because this problem on a scale of interaction of various things, which all of them you checked and they are okay. And here you couldn't check it unless you could test the spec right here. It could be in any place. And so I came to computer science quite late, as a mathematician in 1982, came to computer science and discovered everybody wants to be declarative, especially in Europe, especially in Oxford and Cambridge, but I'm sure, I would guess Amsterdam is no different. So declarativity is like socialism for another world. Good by definition. Never mind what, it's good. You want to be declarative. Socialist politics, I grew up in the Soviet Union, so you can understand this. And what does declarative mean? Declarative means high level, which is wonderful. But a book, you write a book. And there are such companies, especially in England, that so you give them what they want to do, and they write a book. And in 100% of cases, the book is by and large useless. Okay. I say by and large. If you read the book, typically it's good people that understood something. You can learn something. But for the purposes it's designed for as a spec, it's completely useless. Because it's a book, you cannot test. How do you test the book? That's one thing. Another thing, by the time they wrote a book, software changed. Software is, it is not like mathematical problem which waits until you decide. It evolves. It's more like a biological body. It keeps evolving. And so probably their book was never a good reflection of the state of software, state of the system. But it's certainly not good reflection by the time it's finished and brought. The third, kind of small, but also important, engineers can't read the book. It's a thick mathematical book. There are computer architects, they, in principle, can read, but they don't. Why would they waste their time? Okay, so in abstract state machines was the idea, Turing had no chance to do this. At the time of Turing, it was about computability, not about computing. For example, you may have heard that, say, Matei solved with Raphael Robinson, but Matei was first. So to solve 10th problem of Hilbert, it improved undecidability of Diophantine equations. But Hilbert didn't pose the question, are Diophantine equations solvable or not? The 10th problem of Hilbert was solved. Give the output. But by 1980s, when I came to computer science, there were many level abstraction. People in software engineering, people were interested in computing, not in computability, but in practical computing. And in practical computing, there's many level abstraction. You take any this computer. It is not a computer. Somewhere there is a computer. So it has electrical level, it's assembly layer, machine level, assembly layer, layer of programming language, layer of various macros. There's a lot of layers. So when I came to Michigan, it was a strange time when there were no computer scientists. It's very early time. But somebody had to teach this discrete math. Mathematicians were not interested much. And so they hired me. I was a mathematician with no pretense. I wanted to become a computer scientist, but I had no ambition. I didn't have no pretense that I am. So they hired me on the promise to become. I promised because that's what I wanted myself. And in a few days, I went to my chairman and said, I want to give a programming course. I said, no. Why not? He said, we have plenty of people to teach programming. We hired you to teach theory. I said, wait a second, if I will teach theory, I will never become a computer scientist. So he considered it and said, once. So I gave this course. It essentially was Pascal. And then I discovered that there is nobody knows what Pascal is. There is no standard everybody has to comply with. So I had a little Macintosh, Pascal compiler, and University of Michigan actually competed with IBM. They built a huge, big computer. IBM used to still sell some. What? Mainframe? Mainframe, yes, thank you. And mainframe also had compiler for Pascal, and often we disagree. Typically, Macintosh compiler would say, no, it's illegal, but just make mainframe compiler fine, it's legal. So who of them is right? And if students will ask me, well, I don't know. Fortunately, students never arrived to these fine questions. And then I looked all the papers in algebraic specification, denotational semantics. They all study things which are clear, intuitive. But there are dirty, difficult things in say, in C. So I wanted to understand what is the main problem in computer science. And it seemed to me that the main problem is algorithm in the following sense. Physics studies elementary particles, chemistry studies molecules. So what does computer science study? It's not natural science. You study artifacts. And each one of these artifacts is a kind of algorithm. Operating system is an algorithm. Mostly sophisticated scheduling, but it's an algorithm. Databases, if you look, it's actually an algorithm. Not as algebraic data structures, but working database is an algorithm. And compiler is an algorithm. It takes you, programming language by itself is an algorithm. It takes your data and your program, particular program, and runs this particular program on that data. So everything is an algorithm, and now what's an algorithm? That seemed to me kind of key question I tried to understand. And at the time in 1980s, it was obvious the algorithm could be an obvious level, various levels of abstraction. And abstract state machines, which I'll say a few words in a moment, were such that all these were algorithms, high level but algorithms, and you could test them. So if you have this written in abstract state machine. It is a little program, and you can test with the real system because you have to algorithm here, algorithm there, and you can test. And that's what attracted them. It's okay. Essentially history. So now I will give definition of sequential algorithms. So informally, this the only algorithm that existed from time immemorial till 1970s, when eventually community invented highly parallel computer machines and algorithms, and then many other. But these are classical algorithms that what logicians call when think about when they speak about Church-Turing thesis. So the definition will consist of three postulates or axioms, which I will describe now. So the first postulate is kind of trivial. So you have a set of states, a subset of initial states, and a transition function. One less obvious part, which people typically don't mention when they study such transition systems, is that you depend on environment. So, for example, like in Euclid's algorithm, if an environment always honestly computes mod, that you can forget about environment, and mod is built-in function. We call such function static. Static in the sense that you don't change it. So in this theory, there are dynamic functions which are like variables, but variables may have parameters of their own, so general functions. And there are static functions.
To make this a complete definition, you would also have to say something about what type of object is the environment itself, have its own set of possible states.
No, environment is kind of black hole with whom you interact with it. And no, that would be infinite. Yes. I should say that we did. So today I explain sequential algorithms. We have a notion of interactive. And then we don't say what environment is, but there's a clean separation. So here you say, I want to compute mod, and implicitly operating system intervenes. So in our this interactive algorithm, you send the message to the environment. So that's what I need. And the environment sends the result. Now, environment is not guaranteed to play by the rules. It may send you something that you don't understand. There are all kind of errors. Now, typically people consider almost always a clean case when the environment works as intended, and then you can forget about it. Okay, abstract state. So what is a state? State is a description, static description of kind of reality. And logicians, especially in the 1930s, especially Alfred Tarski, analyzed and came up with the notion of structure. So since it's math departments over here, if you go and catch a mathematician and ask him what he's working on, whatever it is, topology, graph theory, it will be some kind of structure. They often call first order structures, but this is the structures. First order structures. Any other structure, second order, model, all kind of other structures, special cases. Structures. So coming from logic, that was quite natural. And structure tells you something about your level of abstraction. So it has vocabulary, finite vocabulary, and this vocabulary may have difference or mod or all. And this, it tells you not all, but quite a bit. So intuitively, a state is all the information which is there. So if environment always behaves the same way, then from this information, you know all the rest of the computation is kind of determined. And it's always determined up to environment. In textbooks, they often say that it's given by values of the variables, which is not correct. It is too simplistic. Because, for example, in C, you may have some procedures, and so which you push down the stack, which have their all kind of variables there, invisible. So this was a big distinction, achievement methodologically, that you concentrate only on the variables and don't think about something that you pushed into the stack. But formally speaking, you need all the information. Okay, that took me a while to came up. So the idea is that in one step, you do bounded work. Unfortunately, I didn't know at the time. Later, I found out Kolmogorov in the 1950s gave a talk in Mathematical Society, and he said algorithms compute in steps of bounded complexity. And then he and his student Uspensky wrote a long paper about it, but I think Uspensky never understood the intent, and the paper is very detailed and all correct. It's not clear why it is. So in justification is we just want to convince ourselves in validity of Church's thesis. But Kolmogorov had something else in mind. He looked at algorithms from the point of view of physics. What can you do in the physical world? Unfortunately, he didn't succeed to put it in three-dimensional space. He did finitely many dimensions, but a priori unbounded. In any case, algorithm is sequential when you do little work, bounded work at one step. If you think about, say, Turing machine, what does it do in one step? Actually, it does three things. Reads, possibly reads, possibly writes, and possibly moves. And no more. So I will not justify it anymore. Now, sequential abstract state machines. There are just these three. So this is assignment. There are functions to which you assign, they call dynamic. These are parallel, oops. Sorry. This is something strange. This analysis, my analysis showed this parallel execution is extremely important. For example, the same Turing machine, it does three actions at a time in parallel. So the idea that sequential algorithm do one action at a time is wrong. It does several actions, but not too many, bounded many. In terms of Turing machine, just three. So it's a very important construct and in general neglected. And then leave the names. That's all. And of course, this is a sequential algorithm, and every sequential algorithm is an abstract state machine from the point of view of behavior. same state, same initial states, same transition function. No, syntactically, they may be given different. And the theorem is that every sequential algorithm is a sequential ASM. So that was the main theorem. So in practice, you can use, and people do use, syntactic sugar. So we will be using some syntax for initialization, input to show what the input is. You can use sequential composition to, within a step, we'll use for loops and for all quantifiers, all bounded. You'll see examples. But in principle, those three commands suffice. So here is, no, second part. What are quantum circuit algorithms? Now, this is QSoft seminar. I copied, I gave previous incarnation of this talk in Paris, and there were many people who never saw anything quantum. So you can actually explain, just think about H as some kind of gate. That's something. So this is an example. Something unusual, this example, it computes C0. C0 typically taken as one of the given gates. But in some measurement-based approaches, you compute C0. So this is borrowed from the literature. Okay, we had to fix some trivialities. So let's see what is important for me here. Notice this. So this is parity measurement. Please don't hesitate to interrupt and ask. I'll presume that it's understood. If not, so this is another parity measurement, and this is standard measurement, computational basis.
What is the outcome of the measurement? Like typically the parity measurement spits out one bit, which is and it collapses on the subspace corresponding.
Exactly. Yeah.
Here there's like two wires coming out on the right side of the.
So you can say it's collapse, but what is collapse? So in terms, let me see. Let's consider this more trivial example.
Two qubits that are measured now, parity measurement. Like a bell measurement. But then there should be like three things coming out, namely the two qubits of measurement.
Classical thing is just the P.
And like the P and the Q.
Let me explain a simple example. Here is, in principle, you collapse, there's nothing should get out. But you get O01 qubit. You get, when you collapse, you get certain quantum state, and that's what get out.
So the R is like the classical measurement outcome, 0 or 1.
So R is, measurement has two outputs. There is a quantum output and there is a classical. So P, Q, and R are classical outcomes. So P gets out and used here. So there is a classical channel. Q gets out and used here and there. Two classical channels, and R is also used here. So this is a classical output. But collapse or not, at least in principle, the number of lines remains. So here is presumably nothing, but one line is there. Just whatever you collapse, it's still. So similarly here, it is two qubits state, and therefore two lines go out. So what for future, what I think important for me, notice that let's say people use different syntax. So I really don't think about peak as classical channels. Rather, I think about them as broadcasting. It's more convenient, so you don't have to write to draw channels. I don't know what these people, they certainly didn't draw the channels to make picture easier to read. Now, what's important here is that this node has two unitaries attached to it. One is Z, which is used if Q is 1, and another is identity. Maybe trivial, but nevertheless. So there are two units. Here there are 3 units. So it could be X, it could be minus X, and it could be identity. So in general, a gate is maybe assigned more than one unitary. In fact, not only unitary, they could be measurements. Okay. So here is standard teleportation from Nielsen and Schwang. And so here you have explicit classical channels.
Yuri, I didn't understand that point. Why it's this? Why can it also be the identity on the previous slide? You said is gate on the top.
So let's see, if Q is 0, then you do nothing.
I see.
Gate that's controlled by the classical bit.
Yeah, I see. Sorry.
Okay, so Andreas and my collaborator, Andreas Blass, in math department, Michigan. So we come from logic. So one thing logic wants precision. You want to have clear definition that you can understand. We couldn't find a definition of circuit in the literature. So people say it's like Boolean circuit. Well, it's like Boolean circuits, but it's quite different. Some people say that every gate is reversible, which is not true if it's a gate is measurement gate. So they say so because they restrict attention to circuit where you measure at the end, forget about measurements, but nobody says that. So we sat down and wrote a syntax. It's also important details, but important that it's written down, you can refer to it and precise. Try to make it more elegant. That's not so important. Now semantics. For theory, to simplify things, you can think about unitary gate as a special measurement with no choice. No, what is a measurement? You have what Schwang Nielsen called a general measurement. So you have some operators such that the sum of unit now if there's a finite set of indices, if this capital I has just one element, then this by definition will be a unitary transformation. So for practice it means nothing, but for theory it simplifies. You can speak, every gate is a measurement. It executes a measurement even if it does unitary transformation. But as we saw, a gate may be assigned several measurements if it has classical predecessors, if it has classical channels coming to it. So in complete generality, a gate has some number of measurement assigned to it, which is one if there are no classical predecessors. Otherwise, at runtime, one of the measurements is chosen depending on the classical results previously computed, and this particular measurement is executed. If you think in terms of engineering, execute things. So this is kind of intuitive idea.
Are you saying implicitly that every gate has a quantum input and a classical input?
Yes.
And it has also a quantum
No,
output?
not some gates don't have classical input. If it's saying unitary transformation, then there is no classical input. Or we can say classical input is 0 and it's it. But yes. Turns out, you can say, what does a circuit compute? Boolean circuit computes some Boolean function. Turns out that any Boolean circuit computes some measurement. So, and you can prove that in general, there are many ways to go through. The execution may have many ways to go through the circuit, depending on when you execute a measurement, then there's a choice. Depending on this choice, branch, you branch, and there is another measurement, you branch again. So there's many different routes through the circuit, but the measurement you compute is the same. So essentially, it's if you take any route, in this route you compute one linear operator after another, string them all, and that would be this A sub pi, where pi is the route.
So by a sequence of classical bits, which are measurement outcomes.
No. You can say classical bits. This essentially the indices. Each time you choose a index, so you take A sub I, and then you take A sub j. That's actually not never used this. Okay, so now go through our circuit. I'll show you the language, the programming language. So this is a circuit. We describe circuit on that level, on the level of diagrams. So this is our syntax for input. And then what do? You execute Hadamard gate on line 2, on wire 2. Then you execute measurement, parity measurement on lines 1 and 2. And you have classical output. Then you execute in parallel. You see how important parallel you need. So H2 and Hadamard gates on 2 and 3. Okay, and so on.
We also just do the, do it sequentially, get to H2 and then H3.
Yes. So here it is, instead of often in abstract machines, we just give one step and say, repeat the step. Here, each step written separately. Because quantum circuits are I forgot mathematical terms. There are only so many steps. No, in this case, what? Less than 10 steps. Yeah,
You step, is it one gate or is it like one time slice?
one time slice.
I see, okay, so you're really counting the depth of the circuit here.
Exactly, yeah. So the parallelism here is bounded by 3 in principle, because there are 3 wires. In reality, it's bounded by 2, but in principle. And right, so in one step you go from the initial state to this state after H, then another step, and you know, that's exactly like in Chang-Nielsen. So they would give many examples when they compute what circuits do, and they give sequence of these global states. So here's teleportation. You see node on the first 2 wires. Yeah. Okay. So one. Fourier transform. So here n is fixed. We speak about one circuit. So the next problem is to speak about families of circuits. And classical definition of families in computational complexity makes little sense for quantum case. What is the classical definition? You use polynomial time or log space to construct circles. Now, if this is your definition, you have somehow constructed in your programming language, all the Turing machine should be there, which constructs.
Isn't this how BQP is usually defined? As like an element of BQP corresponds to a uniform family of classical
Yes.
circuits? Where
Yes,
the
but
classical description can be generated by a log space Turing machine.
yes. But I think that in quantum, this is excessively general. General. I don't know any sequence of circuits in the literature which isn't given just by parameters. Like here, just this parameter n. Let's see, there may be n and k. There is nothing else. So a task to understand how to define uniformity in terms of parameters. Obvious, sort of, in a sense, one way it's obvious. The interesting thing is why it is sufficient. It's just a level of state of art, but I think it's much more than that.
But you need, I mean, there are complicated quantum algorithms that really need like a Turing machine to produce the circuits for input length n and to produce the circuits for input length n+1, etc.
I would be interested to see such where you really need quantum machine to produce. I think it's always much simpler.
No, you need a classical log space Turing machine to generate the description.
Yes. This is a classic, because what this definition was borrowed as is from classical complexity theory, where people don't compute it. They just prove theorems. But if you actually compute and you look what is used, so I looked quite sophisticated circuits which I use Microsoft for complicated involving chemistry and all. I never saw anything more general than just parameters. If there is more general, it would be interesting to see. So my impression is that it's a kind of roof definition, but it's too general. Because if you want to have a good programming language, you have to account to this construction. And so it's such a dirt, you really don't want to deal with that. And I never saw that anybody does in quantum. But that's something we one of project may work on. So here is quantum Fourier transform. One problem with circuits as they So one can say, why do we need programming language? Here's a circle. One problem with circle, you can draw only so much. Children. So let's see, already this circuit has, you see, dot, 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 dot. You cannot write it because you don't know n. So n is fixed, but we don't know what it is. Now, that's borrowed from Chang'in, Lisa Chuang. Yes. In logic, there's a famous book, Chang'in Kissler. So that comes to my mind. Now they emitted swap gates at the end. And then we have to swap the first wire with the last, second with the penultimate, and so on. Now, in this language, usually you use a little syntactic sugar. So we use for all, but only bounded for all, from 1 to n. So n is here fixed, like 17, or whatever. So for all I from, say, 1 to 17, do. Now there's a kind of for loop, but also bounded from 1 to n. So here are the two parameters, k and h. And
What's the difference between for all and for? Is it one of them is somehow?
oh,
like
for is like in programming, like until. For it's a counter, both are counters.
But is there any distinction?
So it is the tradition programming languages. When you count steps.
No, but between the for all and for. Like,
Yes, I'm explaining. So for is used in tradition of programming languages. For is used to count steps. So it's for steps from 1 to for 200 or something. Or if you don't have upper bound, you say until some condition is satisfied.
is the for all is in parallel?
Yes. For all is like logic quantifier.
I think there's also a typo in the last line. It should not be for all I equals 1, but it should be for all I in. I think that's like.
Yes. Correct. Okay. Good. Thank you for the debugging.
I guess you can parallelize the for alls, right?
Yes.
I'm sorry, so like this first line, is that, I guess, in principle, you can imagine during computation, you want to have some extra ancilla qubits, so you would in the middle also declare there's some more qubits coming in.
So here we don't do it. We have a fixed circuit.
So this declaring the qubits only happens in the beginning.
Yes, yeah, because that's how these are quantum circles, as they are. Or,
Yeah, but maybe you measure and you don't need it anymore, and then you want to recycle it.
well, I agree completely. So let's see. Historically, I first formalized this sequential before quantum. It's still 80s, I think. And I conjectured that these three, what I call now ASM language, that this will suffice for all cases. This was a thesis. Eventually was proved in the year 2000. But then we started to generalize more direction. So unbounded parallelism and interaction and some others. So whatever people do, there are restrictions. You cannot do most general algorithms. In principle, you cannot do it because the notion of algorithm keeps evolving. It's like numbers. What a number in general? For a while, numbers were 1, 2, 3, the numbers. So for the Greeks, they had numbers and they had length. Length were not numbers. For us, length are real numbers, but for Greeks, they were not numbers. Eventually, we understood them as numbers. So it was quantity. And then complex numbers came. They're not quantity. So the notion of number suddenly exploded. Now there is a huge zoo of various numbers, algebraic numbers, and if you go and see what is kind of numbers are used in mathematics, it's enormous, and there's no end to it. People add more and more. Similarly with algorithms. So you cannot specify them all. One interesting thing, you cannot even specify all distributed algorithms. Whenever you see a paper and somebody tells us he proves this algorithm, this protocol correct, this is a lie. It's never true. Why? It's not that he's lying. I think most people are sincere, but there is something implicit which is not said. So you have certain level of abstraction. You think about this algorithm on certain level, and on this level you captured the whole thing and you proved correctness. But in the real world, there are hackers, black hat hackers, and they don't play your game. They don't play on your level of abstraction. They come from below and do something that your algorithm or your protocol has no idea happening. So I worked at Microsoft with some kind of genius young Chinese guy who was white-hat hacker, was breaking all protocols in the world. So I collaborated on one paper, and so we got. I didn't break it. He broke everything. I don't take any credit whatsoever. But as we wrote this paper, there are more of us, not 2, 4, 5. It's a paper in Usenix, which has thousands of references. In mathematics, it's completely unachievable. So, but as we wrote this paper, we got some protocols were broken for Google, for what is called now Meta, for Facebook, and they were quite generous. So you break something, they give you some money. So we get triple amounts from more than one from Google, and the most generous I think was Facebook. That's very important for them. You do for them such a thing that they could suffer enormous damages. So what they pay is just peanuts.
It's also risky, right? Because they might not invest anymore in their own debuggers.
That's probably too much. I'm sure they have their own red teams too, but certain things. Okay, so it becomes monotonous. Just if you can write all these algorithms, my impression is much easier to deal with the code, especially if you want to prove something. One example. So this is Grover's algorithm. You see, to do in many cases they have to do something like this, which it's not a usual syntax of quantum circuits. But what can you do? You have to repeat so many times. Now here it all fits. You see, for all I. Okay, from 1 to. Now to the meat. So I claim the quantum circuit algorithms are traditional sequential algorithms as far as software engineering is concerned. Now, and my student says, what about measurement? How does it perform measurement? It doesn't. There is no algorithm performing measurements. So only God can perform measurements. Nature can perform measurements. So essentially, we have an environment which includes nature. That's why I was objecting was formalizing the environment. And
But it's hard to prove anything unless you actually have a definition of the environment.
the typical proof is that if environment satisfies the following constraint, then, but that's also the reality, because environment can always break. In real world, things can break down, and that's how it is. So if you want to prove, let's say your algorithm work correctly, and something broken, electricity, we don't have electricity. That's a part of environment, but you get an error. Quite an involved theory of various errors, how to recover and so on. So essentially the idea is that we have normal, classical, traditional algorithms, except their environment and their operating system is very sophisticated. So you deal not just with standard operating system on your machine, but you deal also with nature. But that's how it is. But from the point of view of algorithmic point of view, it is not much different from the case of non-determinism we saw. So in this early example, see. So in reality, how did this algorithm work? So there was a person, typically a man, and historically, usually a man, actually, I'm not sure. Now I remember there was this famous, so maybe there were a fair amount of women that better not to go in there. And who actually draw these things and chose. And the algorithm presumed that you choose. And algorithm didn't tell you how to choose. Choose. It's up to you. So similarly here is sort of just simple choosing. You essentially you choose. It's essentially same thing. You choose with respect to certain probability distribution, which we cannot reproduce in general. It's only nature can reproduce. But that's how it is.